Right, so this is a matrices question, and first part we're going to show is non-singular. So you need to remember singular matrices don't have inverses, and they don't have inverses because their determinant is 0, and part of the inverse process is to divide all the elements by the inverse, which you can't do if you want to divide by 0. So we're going to find the determinant. Okay, so that's 1 times 1 subtract root 3 times negative root 3. So that's 1 plus 3, which is 4. And remember, it's a show that. So we're going to need a conclusion. So M is non-singular, and you need to learn that when you do show these, you have to say because determinant of M is not equal to 0. So you've got to state the obvious here. That 4 is not equal to 0. Okay. Even better, if you get in there, so this is an even better way to write this, equals 4, whoops, you'd say equals 4, not equal to 0. Okay, right, so we've now got hexagons transformed to hexagon S. Now, we want to find the area of the new hexagon. Don't worry, we don't need to know the area. We didn't know the formula for the area of a hexagon or anything. So, because remember that the determinant of a 2 by 2 matrix is the area scale factor. So if the original hexagon was 5, the area of hexagon S is 5 times the determinant, which is 20. There is a follow through there if you get the first one wrong. Okay, so now our matrix M is going to be an enlargement with the scale factor, where k is greater than 0, followed by a rotation anticlockwise through 0, 0. Now, determinant is area scale factor. Okay, so that's what determinant does, is the scale factor of the area. But remember that an enlargement is how much you multiply the sides by when you enlarge your shape. So enlargement is the linear scale factor, and determinant is the area scale factor. But remember, the area scale factor is the linear scale factor squared. So we know that the area scale factor is the determinant is 4. So therefore the enlargement is the linear scale factor, must be the square root of 4, which is 2. So that's one way to find it. The other way to find the enlargement is to look at the points. So you remember that the first column of a matrix is where, if you apply that transformation, the point 1, 0 goes, and the second column is the point where 0, 1 goes. So point 1, 0 here would go to 1 root 3. Okay. If it's at 1, 0, it's a distance of 1 from the origin. When it gets to 1, 3, if you apply Pythagoras there, you've got 1 squared plus root 3 squared, then all square rooted, you get that that side is 2. So it was a distance of 1, now it's a distance of 2, so the scale factor is 2. So 2 ways to find that. Once we found the scale factor, we can move on to find the rotation anti-clockwise. So what we need to do with that is we take our matrix M and we're going to take out the scale factor to the front, because you can also write scale factors just as a scalar multiple. And if I take out a factor of 2, that means I'm going to have to divide every element of the matrix by 2 to get that. And then we turn to our formula book, and you can match this remaining matrix up with the matrix for an anti-clockwise rotation. This is in the formula book. So it will tell you that the matrix for an anti-clockwise rotation, because I forgot to copy it in, is cos theta sine theta negative sine theta cos theta. So we match up. So if we've got cos theta is a half and sine theta is √3/2. It's important to check both to make sure that you've got an angle that solves both of those, because remember you can get multiple solutions for trig equations. In this case, it is just the first solution of both, which is 60 degrees or pi/3. So our scale factor was 2 and our angle of rotation was 60 degrees, which is therefore the answers to C and D.